Hey, I think that it is officially time to explain the CPU. I know that the series is called 0 to CPU, but I do not want to end the series with this video. The CPU is a rather important component to the computer, but I feel that it isn't enough to call this video series a wrap. By the end of the video, I may have explained how the CPU works, but you may have more questions such as how exactly would this work with the RAM, or how about keyboard support? How do you write programs for it? I think that you guys get it. So I think that everybody would appreciate the series to continue after this video. But let me know if you agree in the comment section below. So, as some of you know, all of the past videos in this series have led up to this very video. If this is the first video that you have seen in this series, do not fret. I will briefly recap everything as I get to it. If you're feeling totally lost, then you may want to check out my past videos. In this video, we will briefly recap the ALU registers and the multiplexers. Then we'll of course talk about the control unit and how all of these parts work together to make the central processing unit. But before we get into things, I did want to mention the big milestone that we just hit. We recently just hit 4,000 subscribers on YouTube. This is absolutely amazing. I really appreciate all of you who have subscribed and those of you who are returning viewers. Hopefully, before we know it, we'll be at 5,000 subscribers. Thank you again for helping me reach this goal. Alright, let's get on with the video. So what we're looking at is the diagram for the CPU. We can see the arithmetic logic unit here. This handles our math and comparison operations between two numbers. Then we have our registers. These are what holds our numbers. Then of course we have our multiplexers. These are just used for data selection. Everything here should look familiar besides this part right here. This is what is called the control unit. It is what looks at our instructions and then it decodes them. The instructions are broken down into little sections that relate to certain tasks. The code comes into the control unit spits out something that other parts of the CPU can use. We will of course talk more about this when we get to the actual control unit section. Essentially, this really is all the CPU is made up of. This isn't a complex CPU like what we use in our phone, but it can still surprisingly do quite a bit of stuff. When I first started learning about computer engineering, I would have assumed a CPU of this sort could only be used as a simple calculator. But when you pair it with the correct interfaces, you can produce impressive results, such as Tetris or even classic Zelda. I'm sure that you could even get a very simple Raycaster working on this. Maybe not Doom, but a very basic scene with solid non-textured walls and a floor. Okay, I'm going to try and recap how we make the ALU as quickly as possible. If you would like a little more depth, I do have a few videos that explain this more clearly. The first thing that we're going to talk about is how we get to the ALU. We're going to first start off with logic gates. I do want to mention that this of course isn't the only solution to making the ALU. There are many different approaches, concepts, and additions that people can do. Some people like to challenge themselves by building an entire computer using only logic gates, such as the NAND or NOR gate. I'm here to hopefully make things easier to understand. Alright, let's see how quickly I can get through the explanation. We start off with our basic and easy to understand logic gates, AND, OR, and NOT. These are what the transistors make up in your CPU. These each take a single on or off input, and depending on what the gate does, it produces an on or off output. For the AND gate, to have an on output, both inputs must be on as well. Otherwise, the output will be off. The OR gate states that if any of the inputs are on, then the output will be on regardless of how many inputs are on. Lastly, the NOT gate. Unlike the other gates, it only has one input. All it does is invert the current input. So if the input is on, then the output is off. If the input is off, then the output is on. It's as simple as that. So we can use these logic gates to build other logic gates, such as the exclusive OR, also known as the XOR gate for short. When you think of the word OR in real life, it means you have to choose between this or this, not both. That is what exclusive OR is used for. If one of the inputs is on, then the output is on. If none or both of the inputs are on, then the output is on. So it is like we can choose one or the other. With these simple logic gates, we can make something called the binary adder. To start, we'll use a simple AND and XOR gate. First, let's think about how binary works. Binary is a base 2 number system, and we represent every digit as a 0 or a 1. When we add two binary numbers together, we can see that for each place, if it is a 1 plus a 1, then the output is 1, 0. If it is a 0 plus a 1, then the output is 0, 1. If it is a 0 plus a 0, then of course the output is 0, 0. If we really think about this, we can actually see something familiar. If we focus on each bit output individually, we can see that for the left bit, if both bits are 1, then the output is 1. Nothing else. Sounds an awful lot like an AND gate to me. Let's move on to the right bit. It seems like the output is only a 1 if one of the input bits is a 1, which sounds an awful lot like an XOR gate. If we wire them up appropriately and assign them a bit place value, we have what is called the half adder. What it does is add two bits together. What we need to do next is make the full binary adder. Luckily, we can use the half adder that we just made, and simply with this configuration on screen, we can add up to 3 bits. The first 2 bits are called X and Y. These are used for adding the 2 number places, and the third bit here is your carry bit. So when you add 2 bits together and both of them are 1, then we carry that 1 to the next full adder. We can chain a bunch of the adders together and we can make our 16-bit adder. So now if we want to add 2 16-bit numbers, we can connect everything appropriately and the output of the adders will be our number. With that, the ripple carry adder is complete. Maybe in the future, we can make a carry look-ahead adder. These are much more efficient. So what we have next is the multiplexer. Simply, it allows us to select between 2 incoming data paths. For example, if I have data X and data Y, I can use the selector bit here to output either X's data or Y's data. Luckily, the circuit is quite simple, as it is using our basic logic gates from earlier. Now, using this configuration, we can select between showing the input of either X or Y using this select bit here. If we make 16 of these circuits, we have 16 bits for the X input and 16 bits for the Y input. If we connect all of the select pins together, we can now switch between X and Y using only 1 bit. It's pretty cool stuff. The mux is probably one of my favorite components. I don't even know why, it just is. Now we can make it back to the ALU. So, all we really need to do is use the adder that we just made before and a few of these muxes along with a few different types of logic gates, and then we have the ALU. So we'll start off with our adder. Given this current setup, we have X input, Y input, and our output. All this ALU can do is add X and Y. Super simple. What I would like to do next is add an AND 16. This is just 16 AND gates lined up. This way we can compare X and Y. So now our ALU looks a little funky, and it is outputting 2 different operations. This is where our mux comes in. If we connect the output of both the AND and the adder to the inputs of the mux, we can then select whether or not we want to do one of those operations. So now our output is the mux's output. Given this, we have 3 groups of inputs to the ALU, our X, our Y, and then our operations. So now I'm going to quickly add 2 more bits. This is our NX bit and our NO bit. Essentially, if we pass the X input to the mux, and then we pass the inverted version of the X input to the mux, we end up with being able to select between not X and normal X. I want to do the exact same thing with the final output. We can have it not inverted or inverted. With these 2 new bits, if we turn all of the bits on, we have unlocked the X minus Y. In a nutshell, inverting a positive number will turn it into a slightly off negative number. This is because for a number to be positive, the leftmost bit needs to be a 0. Now if we add a negative number to a positive number, we get a subtraction operation. Simple as that. Now, we actually add a not Y operation, and then we can do a Y minus X if we turn the NY on instead of the NX. Alright, lastly, we just need to add 2 more operations. This is our zeroing operation. Basically, if this operation is enabled, then our output on that line will just be 0. This is helpful for a few things. First, let's say I want to store whatever value is in the D register into the A register. I would 0 the Y input and invert the Y input. Whatever was coming through the X input, which is the D register, will now be the output of the ALU. which is connected to all of the registers. We of course have many more operations than what I just listed, but that was pretty much the most important of them all. Whew, that took quite a second. Now that the ALU is complete, we can quickly recap registers. So it starts with this basic idea. I want to be able to hold a bit in a component. So that way when I come back to it, I can look at its data. It starts with a simple logic gate called the NOR gate. It is the OR gate, but its output is inverted. The neat thing about this gate is that if you use two of them and you connect them together like this, you get the ability to hold a single bit of data. This is what is called the set reset latch, also known as the SR latch for short. This input here will set the output to on, and this input resets the output back to off. We can make this circuit easier to use with computers if we simply change how it works. Instead of setting and resetting the latch, we can instead load whatever value is on the data pin. This is what is called a D latch. However, we have one more upgrade that we need. The D latch is vulnerable to instability. So if I say I want to load a value into the D latch, but my data pin hasn't settled properly, then the data coming in could be incorrect. If we use two D latches and have the data come into the first D latch on the rising edge of the clock cycle, and then whatever the data has settled into on the first D latch will be loaded into the second D latch on the falling edge of the clock cycle. That way, our output of the data bit can only be changed when the clock cycle has been completed. This component that we just created is called the D flip-flop. Pretty neat stuff. It is actually our official data bit. So now we can use 16 of these flip-flops, connect their load pins together along with the clock pins, and we have a fully functional register. It is a circuit that can store one number. Mine will be a 16-bit number. Registers are often given a specific task, but we will get to that later when the CPU is being assembled. Some of you may have noticed this board in some of my videos. It is a clock circuit that I designed for PCB and had printed from Ivan, a PCB company. I've been using it in some of my projects and it works really well. So I'm very proud to say that there's no better place to get a printed circuit board than with this video's sponsor, Ivan. I do want to show you how easy it is to order. The first thing that you need to do is export your PCB as Gerber files. Once that is done, the rest is on Ivan's site. If you haven't designed a PCB before, but you still want in on the fun, I have the Gerber files for free on my Buy Me a Coffee. The link to that is in the description below. So once you have your Gerber files, the next thing you need to do is make it to Ivan's page. You can use my creator link in the description below, and you'll be met with this page. It informs you that you are eligible for some nice welcome credits, $60 off of your very first PCB prototype. Once you click the Get Your Welcome Credits button, you'll be prompted to create your account. Personally, I like the sign in with Google feature. Next, you can scroll down here to PCB prototype and select Quote Now. You can select PCB assembly if you would like, however note that this option will not grant you the rewards from earlier. From this page, you can simply upload your Gerber files that we exported at the beginning of this segment, and it will auto-complete everything on this page. Check everything over to make sure it's all correct, and then click Add to Cart. From here, select your PCB and start the ordering process. This is just like every other site, so I will not guide you through this part, but once you put in your shipping and your billing information, you can then place your order. From this point, all you have to do is just wait. And that's it. Thank you, Ivan, for being the sponsor of this video. So we have discussed the components and we know what they do. What we are missing is how the programs directly interact with these components. That is really what the purpose of the control unit is. To start off, we should look at a few instructions. This is a very simple program that I've written for the CPU. It consists of 4 total instructions. It does something specific and we'll figure that out as we go. For now, I really want you to look at things line by line. Do you notice any weird patterns? There isn't anything inherently obvious, but what I'm going to point out is these 2 lines. They both begin with 111. This means something for our CPU. Essentially, it means we want to execute some sort of computation, opposed to something like loading data directly. Now, if you see this very first bit here as a 0, then this means we want to load this 15-bit number into the A register. So, this tells us that these middle 2 lines are just A equals 24, as that is what this binary number is, And this one down here is A equals 16,384. Now, these instructions are called A instructions. The other type of instruction, which is where the first number is at 1, those are called C instructions. During an A instruction, all the control unit does is look at the leftmost bit here. And if it is off, then we say, hey, we're just going to load whatever this is into the A register. It is when we get to the C instruction that things get fun. C instructions are broken down into individual sections. All of the operation bits that make up the ALU, all of the load bits for each register, 3 bits for jumping, which is actually loading the program counter, which happens to also be a register. Then we have a few ALU Y input selection bits between the A and the M register. What we're going to look at first is what the jump instructions do. So each bit for the jump operation has a name, greater than 0, equal to 0, and less than 0. It is measuring whether the output of the ALU matches one of these operations. So, if I enable the greater than option and the ALU output is currently 0, then we do not jump. However, if the output of the ALU is 15, for example, then that would be greater than 0, and we will jump. Now you may be asking, where do we jump to? Well, simply, it is whatever number is stored into the A register. So if the A register is holding the number 8, and the jump condition is true, then we will load the number 8 into the program counter register. We can of course combine jump operations. So if we wanted to do less than or equal to, then we could enable those 2 bits. If either of them are true, then we will jump. It is as easy as that. We can of course do a force jump, which means jump no matter the output. That would mean that every bit would be enabled. Obviously, if we do not want to jump at all, then we just do not turn on any of the jump bits. How this is implemented in the control logic is simply checking to see if bit 15 is enabled, and then checking the ALU's output for any of the conditions, whether a number is negative or whether the output is 0, so on and so forth. The next 3 bits are for loading values into our register. What it means is that whatever the output of the ALU is, that will be stored into whichever register is enabled here. So if I wanted to load the calculation into D and M registers, I would simply just turn those 2 on. That's it. So the implementation of this is very simple, just using AND gates. The majority of these operations have to see if bit 15 is on so that we know it is a C instruction. However, we know that the A register is loaded when bit 15 is off. So we have an OR gate that checks whether or not bit 15 is on and whether the load A pin is on the C instruction. Now the names for the next 16 bits may look familiar. That is for our ALU operations. We actually don't let the control logic alter any of these pins. They just go directly to the ALU because there's no need to change them. Then we have our AM pin. Essentially, this is my Y input for the ALU selector. I can either use data from register A or the M register. By default, it is A, but when this bit is enabled, then we use the M as the Y input. With that, you may be thinking to yourself, how can we do A plus M operations? The answer is, you can't. There really isn't much of a reason as to why you need to do this because the 2 registers work together to access memory. Finally, we have our last 3 bits. Can you guess what these 2 do? Absolutely nothing. I'm using the hack CPU architecture, and they haven't planned anything for these bits. You can do many things that you want. I personally wouldn't mind to add an extra ALU operation, or even an extra register. With all the bits cleared up, we can now officially decode our last 2 instructions. Line 2 is actually D equals A, and line 4 is M equals D. The full program should now be seen. You may be asking, what does this even do? Simply, it draws 2 pixels on the monitor. That's it. I would love to explain how that works in this video, but we can't get too off topic. So now, it is time to talk about this mess down here. This solves a problem that the hack architecture did not have an issue with. The computer can't retrieve and store data from RAM at the same time. The hack computer can in NAND to Tetris course, but here in real life, it can't unless if you want to spend extra money on dual port RAM. To save a few extra bucks, you can make your CPU run 2 cycles on the same instruction, when you need to read and write to RAM in the same instruction. It doesn't really solve much because you can just avoid doing this in its entirety, but if we want hack assembly to work on this computer, then we must include this. For this operation to work, it uses a D flip-flop to check whether or not we are doing a read and a write. If this is true, then it will stall the CPU and the program counter will not increment. Once the next clock cycle comes around, the D flip-flop will turn off and the stall will be lifted. And that sums up our control unit. So now that everything is created, we simply just connect it all. We have actually caught up to my real life progress with this exact CPU. Between content creation and my demanding job, I have been slowly making it to the fully assembled CPU. Of course, once it's done, you'll be seeing another full video for it. The issue is that there are a bit more than 250 wires that I must place, but hopefully by the end of July, I will have everything completed and maybe even a new job that is less demanding. But we'll see. So nothing exciting happens with a CPU until other hardware is also connected. The next thing that we could do is add memory. We could also add our ROM. This way our CPU can run code line by line without us having to manually enter it. With those two things, this would then be classified as a computer. Although you may find this computer rather boring, we could connect it to some LEDs for output, or we can even make a few interfaces for the input and output. Maybe that's monitor and keyboard support. With that, this brings the end of the video. I will probably put this series on a short halt until my CPU in real life is completed. I have a few things that I would like to work on, and I feel that this series is at a good pausing point. The game isn't finished, but the quest is complete. I do plan on getting more videos out during July, but like I said, my job is a little demanding and I have to focus on what helps me survive. If you work at a company and you need a software engineer, please let me know. I hope you found this video helpful and hopefully not too boring. I do get carried away with my explanation sometimes, but I do want to think that it's helpful. I do want to thank this video sponsor, Ivan. They have been this channel sponsor for 6 months now, and it has greatly helped fund parts for the projects and such. Alright, I'll see you all in the next video. Bye-bye.